Now, in order to do all this, in order to do calculations at different states, we need to manipulate the enthalpies of reaction. So let's review some of the rules there. So people have gone to great expense to tabulate a lot of these reactions. So we write out, here's an enthalpy of reaction for this particular oxidation of hydrazine. But if we look at the reaction the other way around, enthalpy is a state variable. So if we reverse the equation, if we instead look at the reduction of nitrogen by water, which is unfavorable, but we can certainly describe that reaction to produce hydrazine and oxygen, that enthalpy change in standard state change in enthalpy will just be the reverse of that, because it's a state variable. We're going from top to bottom. If we then go from bottom to top, that just reverses the sign of that state function. And if this happens with exactly half as much reactant, if we look at the reaction for half a mole of hydrazine oxidizing, then it'll take it will release exactly half the heat. So the delta H standard state will be minus 267 kilojoules per mole. And if we have two reactions that occur, like here I've got my reaction to produce liquid gas, and I'm interested to produce gaseous water, to produce steam. If I then then after that do a reaction to go from steam to liquid water, that has an additional enthalpy there. That's an exothermic reaction. Then what I can do is, well, I can double this. That will be minus 82. And then I can add these together. And remember, we don't need to, we can, it doesn't matter how we get from one reaction to the next. So it's perfectly reasonable to have first produce steam and then from that steam produce liquid water. Because enthalpy is a state variable, then it will proceed no matter what. So we can add those together and get an overall enthalpy of the entire process all the way, because it doesn't matter how we get from one point to the next. So this is known as HESS'S law, and really HESS'S law is just a restatement of the fact that enthalpy is a state function. I don't know how you get a law name for yourself when all you're saying is like, oh boy, it's a state function. But that's all it is. If we have a chain of reactions going from one set of reactants to the products, it doesn't matter what intermediates we take along the way. So let's say we're interested in knowing the enthalpy of this reaction, hydrogen gas plus nitrogen to produce hydrazine, okay? But we don't have that enthalpy, but we do have the enthalpy of hydrazine reacting with hydrogen to produce ammonia. Standard state enthalpy is minus 187.6 kilojoules per mole. And we have the reaction in order to be of hydrogen and nitrogen in order to produce ammonia. Okay, well, what we can do is go through a route that goes through ammonia. So let's treat this as an algebra problem. We've got, so we've got 2 hydrogen plus nitrogen goes to hydrazine. And that delta H is an unknown. And we can rearrange this second equation to the producing ammonia to say 2NH3 goes to hydrazine into H4 plus H2 gas. I'm not going to worry about the phases here because everything's in gas phase. Delta H equals 187.6. And then we have 3H2 plus N2 goes to NH3, and that has a reaction, standard state reaction enthalpy of minus 92.2. And then when we add these up, we see that if we, actually we're not going to totally add them up. If we, this is 2. If we cancel the ammonia out, and then you notice that this side has 1 hydrogen, so this goes down to 2 hydrogen, then these 2 reactions added together will be 2H2 plus N2 goes to N2H4, and the sum of these two reactions is the same as that first reaction. Therefore, X is going to be 187.6 minus 92.2 kilojoules per mole, which is 95.4 kilojoules per mole. So what we essentially have done is rearrange the second two equations to find a route that goes from the first set, from the desired reactants to the desired products. So that's how we approach these problems. If we have the right enthalpies of reaction, we can rearrange them to form other enthalpies of reaction we're interested in. So thermite reaction, let's do this with one of our favorite reactions, the thermite reaction. So we're interested in iron oxide plus aluminum going to iron plus aluminum oxide. We want to know what the heat of reaction is. And so let's say we have this tabulated data on the oxidation of iron and the oxidation of aluminum, and we have enthalpies of reaction at the standard state for both of those. So what do we need to do? We need to cancel out the things that we're not interested in. So if we flip flip the first reaction, add the two together, then the oxygen cancels out. Right? Iron oxide is a reactant in the equation that we're interested in, whereas what we're given is iron oxide as a product. So what we need to do is flip that reaction so that iron oxide is on the right side. And also we notice that iron is also properly a product. Well, we keep the second reaction the same. And when we do that, we can see that the oxygens cancel out and we get the reaction we're interested in. So when we have a sum that gets us the reaction that we're interested in, that will just give us the thermite reaction, and we can add together the enthalpies of reaction to get the desired enthalpy of reaction. That is indeed a lot. That number matches with what we know before, that this should be an exothermic reaction. So it's always good to check just to make sure that reactions are what you think.